Right.
Okay, hi everybody, and thank you for attending. And I hope this can be a little bit interactive unless it gets completely out of control. Um, but uh, but this is my usually my title slide, and and I'm an engineer, right? And an inventor. I have a bunch of patents. In order to invent things, you have to read the science. You have to know what the science says. Otherwise, your bridges are going to fall down and your satellites are going to fall out of the sky, right? So we the what so what the science does say is that the Earth is a system is a dissipative heat engine, and we have a heat reservoir. The sun is about 6,000 degrees Kelvin. Empty space is about 2.7 degrees Kelvin, and therefore we right now our temperature is roughly on average about 288 Kelvin, and so the sun is radiating a black body radiator, very highly energetic, low entropy visible light photons, and there's 1,300 watt, 60 watts in this interface right here. And we have to radiate basically the same amount of energy, but we convert it from high energy visible light photons to low energy, high entropy infrared heat, and um, and so a lot more photons for each of these photons, because these photons are highly energetic and have low energy. You can see by a couple orders of magnitude there almost. Well, maybe at least a little bit. And we have geothermal energy, but you could see that that's considerably lower than the energy that's we're receiving from the sun. So we're largely driven by the sun, everything that happens on Earth, including our fossil fuels, which are a function of buried sunshine, life that just got buried without being decomposed. So the Earth system is a dissipative heat engine, and the human economy is also a dissipative heat engine. It can't be anything else. Now, I'm following Donald Rum. I'm going to talk about epistemology a little bit and follow Donald Rumsfeld. There are known knowns. The periodic table of elements is a known known. Okay, so it doesn't matter whether you don't believe in it. It is what we have when we look throughout the universe, and that's why I took my students all the way back to the Big Bang, because we have evidence for the formation we know that the Big Bang only created hydrogen and helium, and everything else was created within stars and then within supernova explosions and the collisions of neutron stars and things like that. And so that's why we exist, because of all that energetics. There's also known unknowns. We don't know what dark matter is, but we know it's a phenomena that we can observe and measure in dark energy. And we don't know how proteins fold, being more prosaic. There are also unknown unknowns. And if I could give you an example of an unknown unknown, of course, it would move into the known unknown category. But Donald Rumsfeld, what he left off is the things we know for sure, which just ain't so. The historian Yuval Harari says much of what we take to be real is actually fiction. And so our heads are cluttered with a lot of superfluous stuff that just simply isn't true. And the flat Earth. I hope nobody here's a flat earther, but 10% of Americans actually are. 30% more or less deny evolution. Another 30%, maybe it's the same 30%, thinks the Earth is less than 10,000 years old. In fact, it's 4.5 billion years old. These things are physically impossible to be true. It's physically impossible. There's no science or evidence to support climate change denial. The Holocene extinction, it has a name. It is actually occurring, and it is a very fast extinction event relative to past extinction events in terms of the velocity. Not necessarily in absolute terms, but the speed at which we're extincting animals is pretty, and plants and so forth, is pretty significant. Limits to growth was never proved wrong. So this is a fiction that a lot of people believe, but in fact, it isn't true. I did a search, but a lot of people have done a search. You go through the peer-reviewed scientific literature, you're going to find a lot of support, and that that the limits to growth, if you compare it to what actually happened, it actually the standard model actually is fairly close. And given that they were running on a mainframe that had the power of a modern day toaster oven, and they were running on punch cards, it's pretty impressive and much more sophisticated than the neoliberal neoclassical economic models at the time, which was basically the key model was a perpetual motion machine. I don't know if I'll get to show you that, but this is actually pretty junk. So I'm saying that as using physics, but Steve Keen wrote a book called Debunking Economics, 502 pages. It's a marvelous book, and Michael, he's an economist, and Michael Hudson wrote a book called Economics is Junk, and he's also an economist. The key about Steve Keen and Michael Hudson, out of all the economists, the hundreds of thousands or whatever economists that exist in the earth back in 2008, only 12 of them forecast a credit crisis, and Steve Keen and Michael Hudson were two of them. So they have some credit to their name. So and again, we'll see, this is not something I'm saying. It is something that seems to be demonstrated by the evidence. Ecological economics, on the other hand, is actually science. And Milton Friedman himself, even he says it, and he is the most influential economist since World War II. And he said you have to separate the economic. He's arguing about the Club of Rome's limits to growth. And he has to separate, you have to separate the economic from the physical point of view when discussing oil. Well, no, how much oil there is determined by, science, by the USGS, by geology. You have to go out and make measurements. It's all physics. Economics can't discover a barrel of oil anywhere. And the fossil fuel industry does not rely on this. It relies on this. And then he calls them stupid projections, and he says they use a purely physical approach, which is arguably the only approach you should use without taking price into account. So I want to point out that price does not signal scarcity. It does not signal value. I mean, you could put a value on a bottle of water and it's not very beneficial to humanity. You could put a price on a slave, but that doesn't reflect the value of that human being. And in fact, we have been involved in slave markets since before Hammurabi. Price is reactive. It reacts to yesterday's news. It's not predictive. And in fact, here's the price of oil over over the last 10 years. It's all over the place. It's $20 a barrel. I think it went to zero here at one point. They couldn't give it away because they didn't have any place to store it. And it goes up to above $120 a barrel. And it's not reflecting the value of oil in terms of its true value. The amount of energy you can acquire from a barrel of oil is exactly the same here as it is here. Okay, so this is not reflecting its value. It's not reflecting its scarcity, and it's not reflecting, it's not predictive of anything. It's reactive. Roger Penrose, sticking with that theme, Roger Penrose, he wrote this is a magisterial work, The Road to Reality. And again, it's a very difficult book to read. We need to address the question of separating true from false before we can adequately attempt to apply such understanding to separating good from bad. And if you think about it, if you can't tell the difference between true and false, how are you possibly able to have a moral judgment, to evaluate morality? I give three examples. We're probably not going to get to them, but I give to my students anyway. Racism. There is actually no such thing as race. You can look up in Wikipedia. There's only a single race. Homophobia. About 1% of humans are born with indeterminate sex, and that's happening increasingly. That's becoming increasingly prevalent because of endocrine disruptors, and so the chemicals that women are being exposed to when they're pregnant, the fetus is disrupting their ability for not just reproductive evolution, but everything else. So it's been linked to autism and so forth. But to be prejudiced prejudice hurts people. And to be prejudiced against kids who are transsexual is violent, and it's unnecessary. I mean, they should give it up. But if we understood this physics, I think we would realize that these things are immoral. This is immoral behavior. And the same thing with austerity economics. It ignores hard physical reality. There's no reason for it. And it's based on economics that's really not very good. According to the guys like Steve Keen and Michael Hudson. Now, this is the picture of our universe. This is actually our home, what it looks like. This is from the Hubble Space Telescope. And our galaxy, the Milky Way, would look something like this if we can't take a picture of it. It's a spiral galaxy. Here's another one maybe on edge. And when I talk to my students, I tell them, the laws that apply to the evolution of this, to the universe, apply to us. You can't separate the human economy from the universe in which we reside. And so energy conversion and entropy production drive life, the universe, and everything. And I'll rely on Albert Einstein, my good buddy. He says thermodynamics is the only physical, I can't even read this stuff. I got to get this out of the way. Physical theory of universal content that will never be overthrown. And Arthur Eddington, who proved Albert Einstein's general theory of relativity, says, if your theory is found to be against the second law of thermodynamics, I can give you no hope. There's nothing for it but the collapse and deepest humiliation. And then if you understand entropy and so forth, David Caitling is an astrobiologist. Organisms spring into existence because of the physical laws. So even the very life itself depends on this. And Rainer Kummel, who's a physicist, wrote one of the best economic textbooks, The Second Law of Economics, Energy, Entropy, and the Origin of Wealth. And he shows by looking at the data that energy conversion and entropy production are determine the growth of wealth. In other words, energy flow or energy conversion, it's not energy itself, but it's power. It's really the flow of energy is the only factor of production, and doesn't even appear in the economics equation for production. And then, of course, unfortunately, energy and entropy are ignored by neoclassical neoliberal economists, and not just them. Steven Pinker, in his book, I forget what it's called. He's energy blind. Most historians, it's a shame, but they're not aware that in the 1800s, when we discovered fossil fuels, that was the takeoff of everything human. By the discovery, we just captured this great amount of energy. I don't know, maybe this is too much. The three laws of thermodynamics, I think it's funny. We can't win is the first law. It just means energy can neither be created nor destroyed. We can't even break even. That's the entropy law. Entropy always increases. This is the arrow of time. And we wouldn't exist if this wasn't true, and if the universe didn't start in a state of low entropy. So what is low entropy? I think the simplest explanation is entropy is the opposite of free energy or exergy or potential energy. So when the universe starts with only hydrogen and helium and a smattering of gravity, that gravity can begin to pull that hydrogen and helium together. That's a gradient, gravitational gradient, and the hydrogen and helium into stars. And as the stars compress and get hotter and hotter inside, they ignite the hydrogen and the helium, and you get fusion. Because we have to have that compression. You have to have that gravitational compression to initiate, to overcome the Coulomb force. That's the fact that hydrogen and helium nuclei are positively charged, so you can't push them together. It's like putting two north magnetic poles together. You can't do it. You have to overcome that force. Anyway, that's the scheme. That's why there's something rather than nothing. And the third law is about the definition of absolute zero, but basically it says we can't even get out of the game. And the fourth law is the maximum power principle. And this is, not all physicists, I have to tell you, do accept this as the fourth law of thermodynamics. It was proposed in 1922 by Alfred Locke and expanded by Odom and Pinkerton, and more recently by Hall and McWhirter.
Did I lose you, Tony?
Did I hear a question?
Sorry, it just froze up a little bit. I was wondering if we lost you. Maybe it was
Oh,
my
no, I'm here. My
joint.
internet connection is unstable.
Is it?
Okay, well, here we go. Let's
Yeah.
see.
Sorry, I didn't mean to interrupt you.
No, that's okay. So, Hall and McWhirter wrote a paper. This is a really good paper. It's not too difficult to read if you have some science, maximum power in evolution, ecology, and economics, and it's philosophical transactions. Okay, so this is probably difficult stuff, but it's necessary stuff to understand, and my students could get it. The other reason I went back to the Big Bang is to focus on limits. The speed of light is a limit, Shannon's limit on information transfer. Of course, my students really like this because they're going into IT, a lot of them. Carrying capacity of the Earth is the Carnot heat engine efficiency, and so forth. There's limited resources and certainly limits to growth on a finite Earth is a fact. And that's why it was never disproved, because no economist has ever found that that energy and resources are infinite and can support infinite growth, right? Exponential growth forever. And then of course there's maximum entropy. When we reach that, that's the end of the universe. So now I want to switch and talk about history of the Earth, and and I'm going to focus on the end Permian extinction event, because this is the closest analog to the Holocene hypothermal. We are creating the same conditions that existed at the greatest extinction event of all time, 250 million years ago, plus we're adding a bunch of other stuff that didn't happen back then, like endocrine disruptors. Then there's the mid-Miocene, 15 million years ago, had the same level of CO2, but was 6 degrees hotter. And that's scary because it shows that our climate is in a bistable state. And so we can, this level of CO2 is compatible with the climate we have now. Plus, but it's also compatible with a climate that's 6 degrees hotter. And we'll talk about why that is when we get there. And the Holocene climate is showed without any doubt that civilization is very fragile. We are causing all the stresses which have collapsed civilizations in the past. Civilization depends on agriculture. Agriculture depends on a stable climate of the Holocene. And we have 8 billion people now, 9, maybe 10 eventually. And we can't feed them without modern agriculture. And we certainly can't feed them if we lose the stability of the climate. I've just read this paper. It was published 23rd of May, so it was only a few weeks old. 66% of global population is going to experience water scarcity by 2100. Okay. If 66% of the global population is running short, they don't have water to drink, the economy is going to collapse. Okay. We have to avoid this at all costs. We have to figure out how to do that. Ultimately, when we go through the data and the numbers, we're going to have to give up on fossil fuels, and we have to do it as soon as possible, because we can't allow this to happen. We can't allow this to happen. And we cannot replace all fossil fuels with alternatives fast enough. There's just no way. We don't have enough mines for nickel and niobium and everything else. And we can't open mines fast enough. To open a mine, you're talking 10 to 20 years, and you got to go through all kinds of, and a lot of people aren't going to invest in it because they don't know if it's going to be profitable. you're not going to pull anything out of the ground for 10 or 20 years. So we have an economic system which is a failure anyway, and we have to degrow the economy, because if we degrow the economy, then we rely less on total energy. We get it down to a point where we actually can replace fossil fuels with alternatives. Of course, that means we have to value, you know, we can't be producing junk anymore. We can't just consume for the sake of consumption. We have to actually, target. We can't have design products to not work anymore after a couple of years. The Earth is in fact a thermodynamic system. This is the Thermodynamic Earth. Axel Clyden's book is kind of a difficult read. It's a graduate level textbook, but I think his YouTube lecture is pretty easy to grasp. Anyway, we're gaining solar radiation, like I talked about before, and we're losing heat. And when those things are balanced, that means the temperature of the Earth is balanced. And the solar energy drives everything: heat transport, buoyancy. It's driving the currents, the wind, um, you know, uh, life, everything. And then down below, of course, we do have that heat generation, geothermal energy, which I mentioned, and half of that is the pressure of gravitational pressure. So the center of the Earth is about 6,000 degrees, almost the same as the sun's surface. And there's a lot of radioactive decay of uranium and phosphorus and radon and things like that. And so that's generating heat. And even though it was a very small number compared to the sun's energy, it's enough to move continents around. Biotic activity exists on a thin veneer of the Earth's surface, and then human activity is a small part of biotic activity, or actually it's an increasingly large part. But it depends on things that go in and go out. And now here's something that is critically important to understand, because if you understand this, then you understand why a lot of denial arguments are in the face completely wrong. And we knew that the sun worked on fusion back in the 1920s, so for over 100 years, I think. But the details we didn't figure out until the 1960s. And in the 1960s, when we worked out all the details, we figured out that any star, not just our sun, but any star, starts out with low luminosity and just ever so gradually gets warmer and warmer and warmer. And most stars are extremely well behaved. This is a very monotonic function. Some stars are not well behaved, but ours fortunately is. Life began roughly 3.5, 4 billion years ago. At the time, the sun was only 75% as bright as it is today. When we talk about the end Permian, which I mentioned before, the sun was 98% as bright as it is today. That's 250 million years ago. We'll talk about that in a minute. Okay, so the faint young sun paradox is how is it the life form? How could there possibly been liquid water? The Earth should have been frozen over solid. It should have been hundreds of degrees below zero, or 100 degrees below zero anyway. And so why do we exist? And the answer, of course, is now remember the sun is heating up because we're turning up a thermostat. The universe is turning up the thermostat on the sun. And obviously we had a lot of blankets. And what were those blankets? The partial pressure of CO2. And back then in the day, there was between 1,000 and 10,000 molecules of carbon dioxide for every molecule that exists today in the atmosphere. And that was enough of blankets to make up for the faint young sun. But unlike the sun's nice steady what do you call it, thermostat, it came up and the carbon dioxide and also a little bit of methane and other things were pulled out in fits and starts, but always stayed within the bounds that liquid water existed on the planet. That's amazing. And this was the foundation of the Gaia hypothesis of Lovejoy, and I think it was Lovejoy, right? And Carl Sagan's wife. I can't remember her name. But anyway, when it was up here, we had a hothouse climate, and when it was down here, we had an icehouse climate, which we exist in today. We have an icehouse climate today, which just means we have ice on the poles. Here we have effectively palm trees. Well, we didn't have that then because only bacteria existed here, but later on, or the equivalent. But anyway, here, when CO2 is pulled out enough, 2 points, the Earth actually did freeze over. At first, they thought to the equator, but now they think it was just not a snowball Earth, but a slush ball Earth. And so life persisted at the equator because there was plenty of liquid water. And so that's what makes the difference. And carbon dioxide is Earth's non-condensing greenhouse gas. It's the most important greenhouse gas on Earth. It's a forcing function. Water vapor is an impressively strong greenhouse gas, but it's condensing, so it rains out of the atmosphere really quickly. It's only a feedback. Let's see. So I'm going to compare extinction events. There have been 4 extinction events caused by organisms, and so 2000, sorry, 2.4 billion years ago, that was the great oxidation event. That's when cyanobacteria, which was a microorganism, they invented or discovered oxyphotosynthesis. Now, photosynthesis actually already existed, but what they weren't breaking up water into hydrogen and oxygen. They were using hydrogen sulfide. This was a much better way to make a living. What cyanobacteria invented, to use water because water was plentiful. And but there were consequences to this innovation. And by the way, their innovation is exactly what plants use today. It was good enough that evolution decided not to mess around with it, and so this is a great innovation for us. So the consequences is they were pulling carbon out of the atmosphere, so the globe cooled, and that's what caused the slush ball Earth back then. And oxygen turns out to have been toxic for the other microorganisms that existed at the time. And so it was a big extinction event, but among microorganisms. There were no cute bunnies then or anything like that. The end Ordovician is considered one of the big 5 extinction events. I think about 84% of species went extinct. It was a pretty big one. And the main event was moss. Now, 440 million years ago, or before this, there was no life on terrestrial surfaces on the continents. Might have been some bacteria, but there was no life per se. It was just rock, and there wasn't much soil because the rock would weather and erode, but the soils didn't build up. But that erosion was what fed the marine environments with phosphorus and nitrogen and magnesium and other nutrients that life in the ocean needed. And so the ocean environment was where all life existed before then. Moss, I mean, there was some life where it was damp, like tidal pools and stuff like that. Moss figured out how to develop acids which could erode rock and release nutrient minerals. They also invented a hard cover for their spores, and so their spores could travel over the rocky surfaces and survive dry spells. So they could expand over the continents. But these acids eroded the rock much faster than they were being eroded by simple weathering, and it caused an extinction event. Eutrophication and anoxia, exactly what we're doing today with our agricultural chemicals. We've created more than 700 dead zones around the world in our oceans and our estuaries, and basically from the weathering of I mean not the weathering, the nutrients that from the artificial nutrients that we apply to our farms that run out off. So we're actually doing the same thing. This caused a big extinction event because for the same reasons that the dead zones that we're causing, that was what happened here. And so that was a big extinction event. But life recovered, and it turned out that the Morse's innovation turned out to be a good thing for the future of life, just like oxyphotosynthesis. 360 million years ago, during the Devonian extinction was caused by vascular plants, and they created a root system, and that root system could increase rock weathering. And again, it's the same thing going on. Once you increase rock weathering by perhaps another order of magnitude, you're enhancing nutrient runoff, and you're creating nutrient eutrophication and oxy. And they also did a number on the CO2 in the atmosphere. So there was also climate change involved. Okay, so what are we doing now? So now we have a single species, an organism, humans, and we got an innovation, a huge innovative metabolism called fossil fuels, chemical farming, overexploitation, habitat destruction, pollution, so forth. But it might go all the way back to Homo erectus, who discovered how to control fire, so 1 million years ago, and that put us on the road to extinction. I don't know, but I think Homo sapiens should take all the credit. Increased CO2 and other greenhouse gases causing global warming, enhanced nutrient runoff, and as we've seen, right? And then, of course, we're throwing endocrine disruptors are causing infertility, not just of us, but of other species. Okay, let me go back. And Permian 250 million years ago. So what happened was in present-day Siberia, there was a major volcanism, and about 10 million square kilometers was covered. I guess we got somebody that's joining us. Okay, we had about 10 million square kilometers of the Earth was covered over Siberia, and that went on for it was fairly slow. It was like 200,000 years it took place. So part of what causes extinction events is, number one, is the absolute values, but more important is the speed with which they happen, because you could get a lot of climate change, but it happens extremely slowly. Everything can adapt, but if they happen very fast, things can't adapt. So what happened is near the end, somewhere along the line, this thing got plugged up, and the magma probably could have burned its way through, but instead it found easy egress into carbon-rich sedimentary rock. In other words, coal. So all the coal was formed during the Carboniferous, which had already occurred. When I teach my students, we go over the Carboniferous, and so the magma burned right through that coal, burn it all up, and it was until it got to the perimeter of this basalt rock formation that it was emitted into the atmosphere. So the amount of carbon dioxide that was emitted is equivalent to about let's say about 4 million tons of carbon dioxide per year. And this is 1 million tons of carbon, 1 billion tons of carbon. So it would be 4 billion tons of carbon dioxide. So enormous amounts of carbon dioxide that it was being emitted that caused climate change and a whole bunch of other things. All the things we're doing today, ocean acidification and everything. And that was the greatest extinction event of all time. Well, we can compare that end Permian with the end Holocene. And what we're putting carbon in is at the rate of 10 billion tons of carbon, or 40 odd gigatons of carbon dioxide. And so 10 times the rate of the end Permian. So every year, 10 times what happened then. But then when you add all our other greenhouse gases, it's the equivalence, it's more like 16 times. And when you factor in the faint young sun, it's you can double it again. So it's more like 30 times the global warming potential. So the total carbon emissions is not as great. but the rapidity with which it's occurring is we're setting a record. This never happened before, and this is guy climate scientists kind of concerned. Uh, and with everything else we're doing, ocean anoxia, hypoxia, the eutrophication, all that stuff, all the cool stuff, ocean acidification. We're doing all this too. This is everything that happened in the Permian we're doing, but we're adding all this cool innovation. So everybody says, so many people tell me, oh, but we're going to be innovative and we're going to innovate our way out of all these problems. And they're looking at me, one of the innovators, because I'm an inventor. And I'm saying, I don't think so. So this is human innovation, right? Pollution, overexploitation, loss of habitat, disruption of potassium, phosphorus, and nitrogen cycles. None of this happened during the Permian. So this is like a major big thing. The Conodonts back 250 million years ago weren't doing any of this, minding their own business, really. Okay, so there's the faint young sun. That's why it's important. Um, and so just a quick aside, where did fossil fuels come from? Buried sunshine. So we didn't see this, but I taught my students anyway that coal all came from trees that didn't decompose during the Carboniferous. Oil from marine life that did not decompose before subduction, all during under the continental plates, all during the Phanerozoic. Methane came from both, but methane comes from other sources. The USGS estimates there is 5,000 billion tons of carbon in the form of fossil fuels created over 500 million years. That's 10,000 tons per year on average, although the bulk of it was done during Carboniferous. But on average, at least, we are using 10 billion tons of fossil carbon every year. So we're using 1 million years worth of carbon every year. It took the Earth 1 million years to create. Well, on average, because a lot of it was created during the Carboniferous. But putting that aside, that just gives you, what can go wrong with that? Okay, now I'm going to switch back forward in time to about 16 million years ago. And this is so you can see if we can compare what we're doing today with the greatest extinction event of all time, right? We need to be concerned. And this is the Cenozoic. This is the last 66 million years. So the dinosaurs went extinct here 66 million years ago. This is atmospheric carbon dioxide, is this, and this is the temperature of the Earth shown graphically by all these bars. And you can see it tracks really, really well. When it was hot, there was a lot of carbon. When it was low, the temperature was low, there was a little bit of carbon in the atmosphere. So it tracks really well. It is definitely carbon dioxide. In their paper, they conclude that Earth's system sensitivity, which is how much the planet will warm if we double CO2, is predicted to be 5 to 8 degrees. This is way higher than the IPCC, which estimates 3.2 degrees. This is paleoclimatology. This is not models. This is paleoclimatology. Now, there's caveats here, but right now we're at 426 ppm, and when you add in all the other stuff, the equivalence is 500. We're at the mid-Miocene, and that's what I said. This was 6 degrees hotter than today, and we have enough carbon in the atmosphere to get back there. So why aren't we there? Well, of course, because we have ice at the poles. And so you can think of the climate as a very complicated system, but we have ice. We're in an ice age, and we have ice on the poles, and we gradually have to melt that ice because it takes energy to melt ice before you can start heating the planet. Well, we're heating the planet, but we're also spending a lot of energy melting that ice. In the Miocene, there was no ice on the poles. I don't know. I think I have a picture of that. I'm not sure. But they were traveling down this way. So the ice gradually was forming, and then they plummeted down to here. So it's like a hysteresis, like a magnet. You've probably seen this kinds of curves in high school. And so, what danger are we that we could flip into a mid-Miocene type climate, which we would go extinct. We cannot handle 6 degrees warming. We're a cold adapted organism. We're not ready for a hothouse climate. Other organisms will survive, but not us. So there are tipping points, and that's why you hear all the time about these tipping points, and it's all in the IPCC report. reports. Tropical coral reefs are already committed for extinction. If you read about in the news, we're having our fourth ever global coral bleaching event and mortality event is occurring right now. And it's worse than all the others, and they're happening much faster and much sooner. So the first time it ever happened was 1998, and then the next time it happened was 2010, and then it was 2016, and now it's there was 5 extinction events since 2016. So coral reefs are gone; they're toast, unfortunately, because we're at 1.6 degrees. And 25 to 30% of marine organisms depend on coral reefs for some part of their existence. And so this is going to be a big hit. So this is going to make the Holocene climate look, the Holocene extinction event look like a big serious one. Arctic sea ice may disappear, almost certainly. Greenland ice sheet may have already passed the tipping point according to these 2 papers I found. West Antarctic ice sheet is also past an unrecoverable tipping point according to Garb. This adds about 7 meters of sea level rise, but maybe not all of it will melt all at once, obviously. So a couple meters of sea level rise. And this is another couple meters of sea level rise. And the Earth system's ability to absorb human-caused emissions could be reduced significantly, according to this paper by Duffy. And she talks about her research here. Okay. These are not the only tipping points. There's about 10 others, but they're projected to happen not this century or not before 2050, but maybe 2100, sometime after that. Okay, this is the third part that we want to look at. So we already, the alarm bell should be going off, right? This is why climate scientists are worried. This is why they keep on yammering off about how serious the problem is. This is the Pleistocene. The boundary between the Pleistocene and Holocene is about 11.7 thousand years ago, right here. And the Pleistocene started about 2.25 million years ago. So all of this beforehand was the Pleistocene. The Pleistocene climate was jagged. It was like this all the time. It varied 1 degree per millennia, per 1,000 years, like all the time. But it always was an ice age. It was always, and so species that were cold adapted, like humans, were fine. I mean, we just had to move, and the ice expanded and contracted at the poles. There was very little extinction due to those changes. There were some, but the big thing is wherever humans went, all the large megafauna disappeared. And it's still, some people would say, well, it's only coincidence. They really disappeared for some other reason, and they try to find artifacts of a collision with an asteroid or something, and they never found one. I mean, yeah, come on, let's face it, it was humans. And it had to do with that maximum power principle, which is hard to explain maybe, but I think I can when we get to it. The point is this kind of change is fine for the biosphere, but fine for humans as hunter-gatherers, but you can't do agriculture when the climate is changing, when the climate is not stable. And so it was not a coincidence that around 10,000 years ago, nearly everywhere humans started developing agriculture. My guess is 1,000,000 years ago, Homo erectus knew about agriculture, because if you have a garden and you have a compost pile, you know that you get volunteers out of your compost pile. Tomato plants and potato plants and everything. Whatever you threw into the compost the prior year starts to grow, right? And you can put 2 and 2 together. Oh, yeah, it's the seeds. I should collect the seeds. But it didn't make any sense if the climate is changing so radically. All of a sudden, we hit the stable climate, pristine, clear, stable climate. And John L. Brooke is an historian, but he wrote it's a graduate level textbook, Climate Change in the Course of Human History. And he gives a lecture here, and he's lecturing climate scientists, and he's saying, "Look, I took your data, and I correlated that with human history, and it just works really, really well." He could explain all kinds of things, but the main thing is that the climate became uniquely stable, almost surreally flat in the Holocene compared to the instabilities of the Pleistocene. And he basically says the transition to food production and agriculture could never have happened, and the entire subsequent course of human civilization could never have unfolded unless we hit that nice serene climate, which unfortunately we're departing from. And the rate at which this is a scary thing, the rate at which we're going here is about 10 to 30 times faster than this. And we're going into a regime where humans are not really prepared, and it's going to disrupt agriculture big time. And I've told lots of people the thing to worry about is agriculture, not sea level rise. I mean, it's going to be a pain in the neck because we're going to have to build a wall in Virginia to keep DeSantis and the Floridians out. But I joke, we would invite them in, but and they'll have to move. But that's not the big deal. The big deal is agriculture. Now, the funny thing is 88 civilizations collapsed in this 4,000-year period. And one of the causes was abrupt climate change. The biggest cause, and the cause associated with every single one of these civilization collapses, is inequality and establishment of an oligarchy. And then there was all these other things. The thing of it is that right now, today, all of these things are in play. We're causing all of these things to happen, whereas these civilizations collapse only by a subset of these things. Each one had a little subset. And abrupt climate change. You look at this and say, abrupt climate change? But there were, the climate changes regionally, and sometimes you get 5 years of a drought, and that'll do in an agricultural society. The good thing is they weren't very far removed from their hunter-gatherer days. There wasn't that many people, and they could move. There were probably almost certainly hunter-gatherers in very close proximity who they traded with, so they knew how to make that living. So the civilizations, I mean, people died, but the civilizations could contract, and then another one would spring up. So it wasn't a disaster that the current one is going to be, because there's no place for 8 billion people to go. The other interesting thing is we have weapons of mass destruction. Lots. Okay. So I mentioned that what time? I don't even know what time it is. Let me just check my time. Oh, 8:22. Okay, I got some time. So the IPCC says the Earth equilibrium climate sensitivity, I mentioned that, right? This is the Cenozoic project, 5 to 8 degrees, is 3.2 degrees. Everybody used that assumption. That's the right thing to do. That's our best estimate, the IPCC reports. That was published in 2019. James Hansen, though, probably the world's top climate scientist, he writes a paper in December and says, no, wait a minute, I think it's 4.8 degrees. And this is his estimate, very likely estimate, and this is IPCC's likely estimate. Okay, so there's a problem. Even in the IPCC reports, this is their models. And so what this is 5 models predicted this, equilibrium climate sensitivity of this, 5 models predicted this, and all these models were up here. So half the models actually agree with Hansen. So it's not like he's not like a global warming denier. You don't see anything here. There's no blocks, there's no paleoclimatology, there's no models, there's nothing that supports deniers. There's no evidence of anything. I mean, that's just fossil fuel industry making noise because they're trying to protect their profits. And, that's what capitalism demands, that you protect shareholder value and make money. So if you have to lie about it, that's what you have to do in capitalism. Okay, unfortunately, that's the system we have. So this is paleoclimatology. There's 2 different studies, the Cenozoic project we talked about, and the Christensen-Totten study. These both covered the entire Cenozoic and plus a little more back 100 million years ago. And then half the models, again, are agreeing with James Hansen. So this is Hansen's paper, December. Okay, now moving right along, CAT is the climate action tracker, and they do a good job. What they do is they look at what all the countries around the world are proposing to do. Their policies, their pledges, their targets, et cetera, et cetera. and none of them are good enough. They have to get down to 1.5 degrees, so they invent an optimistic scenario. The optimistic scenario, not only to get to 1.5 degrees, well, not only do we have to be extremely lucky, we have to have about 10 miracles. So that's not going to happen. But it's the only, but they have to, there's pressure on them to show that we can achieve 1.5 degrees, and that's not going to be possible. But these numbers are based on that 3.2 degrees. If you put James Hansen's number in there, and which I did, it was easy enough to do. We're not even optimistically, we're above 2 degrees. Okay. Uh, and the more likely outcome, the real world uh, thing is 4 degrees, and it goes all the way up to 5 degrees. Um, and they don't include all those tipping elements, by the way. So when these tip elements start to tip, this is just flat, just how much the planet's going to warm. And it is also only by 2100. Even these guys, I mean, they say this is 2100. So it's going to keep warming, except for this one, but that's not going to happen. So we're in serious trouble. Okay. I can't emphasize it too much. We're going to see this again. I gotta look at my time because I definitely want to show you that. Okay, this is these are the planetary boundaries that we've exceeded already. Um, we're no longer in any safe operating limit except for these three guys are still there. And again, when I talk about degrowing the economy, I don't see any other way to pull these things back into safe operating limits because there's all of them. There's 6 of them. It's just too much. You can't do that there's not enough miracles. We're just, humans are just not that inventive. As an inventor, I'm telling you, we're not going to come up with all this stuff. And I look at it's just such good news. We're so optimistic. I see in Wired and all these other places, humans have, some scientists have created this new battery based on this and that. Well, it's always overinflated. It's always over optimized. You go talk to the scientist, send them an email and say, well, did you really do this? Well, not exactly that. Okay, biomass of wild mammals is in free fall. 17% of wild mammal biomass is left. So remember when I talked about those other civilizations, collapsing, and they could just the people could leave their city states and go back into the woods because the woods still existed, and there's still wild mammals to hunt. Well, there's nothing left for 8 billion people to eat in the wildlife. Dry mass of human stuff. Again, by the way, this is a hockey stick, an inverted hockey stick. Here's another hockey stick. There's lots of hockey sticks, and this is the dry mass of human stuff. It exceeds the life on Earth, the weight. Okay, and it just keeps going up. Here's another hockey stick. It's going down the other way. Human sperm counts have declined since 1970, and everybody admits this. Nobody denies this. There's no refutation or anything that we have. The average male today has less than 40% of the sperm count he had in 1970. And this is the endocrine disruptors, it's pesticides, it's plastic, and all kinds of other chemical pollution in our environment. And these things are everywhere. They're in the Arctic, they're at the bottom of lakes, and they're in the oceans, they're in polar bears, they're in our testes, they're in our brains. And we can measure, as Shanna Swan says, this is her paper, but you could Google her name and you could listen to her talk. We don't have record of human ovaries because that's an invasive process to extract ovaries from a female. So, but where a human male can you can get those samples. So we have lots of samples and we can look at that. And again, no one's disputing this, and it's accelerating. You can see in the last 20 years that the trajectory is even lower. So we're creating a population of infertile males, and no doubt infertile females. And so when we talk about the demographics and the population beginning to stabilize in a lot of countries, the fertility rates are going down. They always say, oh, it's because people we're in agriculture and they're moving to cities. And I'm not going to doubt that might not have something to do with it, but people have moved from agriculture to cities and still had a lot of kids. It's a difficult one to justify based on the history of humanity. Um, but they never mention this. And it doesn't just affect our sperm counts and our infertility. It's why a guy graduates from college and has no interest in sex or no interest in women. I mean, his libido is real low when he lives at home with his parents in his basement, stuff like that. And it's also implicit, and Shanna Swan says this in all these the rise in the number of babies born of indeterminate sex, because the fetus are exposed to these things, fetuses, when they're trying to develop. Okay, so it's clear. This is a paper published this year, January 2024. Okay, I love this. It's a great cartoon. The paper is pretty, it's a pretty good paper to read. It's not too difficult to understand. We are on path B. So just like the other three species caused extinction events, we are causing an extinction event. We are heading toward the biosphere collapse. The trouble is, the difference between Moss is we have all kinds of weapons, not just weapons of mass destruction, but we have Uzis and AK-47s and all kinds of things, and bazookas, who knows what, tanks. And so when we get stressed out, we're probably going to extinct ourselves by conflict. And that Morse didn't do that. They just hit this point and died back, and then life recovered after a million years or so. It wasn't that long. But we have a path A. And that's the important thing. There is a path A we have to get to. And in order to get to path A, we have to get off of path B. We can't, when I talked about, I started this thing talking about economists, neoclassical and neoliberal economists. They are holding us to path B. Okay. And we have to get away. We have to get away from capitalism. And in The Economist, Nate Hagens points out that capitalism is the same as communism, Soviet-style central planning. They both require exponential growth to survive. And that's his words, not mine. I don't know much about what was going on in the Soviet Union, but it did grow enormously at the time. But there's and economists will throw that at your face all the time and say, well, capitalism is causing problems. Well, what do you want? Communism? It's not like that those are the only two choices we have. There's an infinite number of choices in between. And some of those don't involve infinite growth, infinite all the time. And some of them are actually sustainable. So we have to find a way to that. So these are known knowns, getting back to known knowns. These are problems. We know these exist. And these are known physical laws. I talked about thermodynamics at length, but there's other laws that we know. And so we are looking for an economic theory which encapsulates the known knowns. They have to capture what's true. And even Milton Friedman himself says, we're not interested in that. All we care about is, well, what they care about is consumerism. Because as long as people consume more, as long as there's more consumers, a lot of these economists are worried that the demographic says we're running out of humans, we're going to stall, is because who's going to consume? They're all about consumption, and we have to stop consuming. Where am I at? It's 8:30, so I've been at this an hour. What I want to do is say, I'll just real quick say there is a discipline of science called ecological economics, and it does abide by the laws of physics. And so economics there is an out for us. These other schools of economics, they understand that well, they fight like cats and dogs. These are oppositional clans or schools, right? These are religions. These are not science. And but these guys all disagree with these guys, and there's some benefit to some of these guys. There's nothing here, nothing relevant to our survival. But ecological economics is the only discipline of economics which is open to anybody. You can publish in an economic literature as long as you tell the truth. That's all you need to do. And so a lot of these guys do publish, and none of these guys will. I don't think they will, but these guys will. Okay. This is a list of things that the economists get wrong. I have charts on all these things, but we're not going to do that. And so this is the real problem with neoliberal, neoclassical economics, orthodox economics. They want to maximize consumerism. They're maximizing the flow of money and GDP. To Friedman, and if you read his book, he calls you a consumer unit. If you feel like a consumer unit instead of a father or a mother or an uncle or an aunt or something like that, well, God bless you. Um, and they want to maximize private profit. Why does there have to be profit at all? Why does it have to be private? Biophysical or ecological, heterodox economics, the economics that we really want to drive, every human should have a decent life. But not only that, we want to preserve the environment and resources for future generation, preserving the environment for co-evolved species. This is not against science and technology. They accept science and technology advances. These are not Luddites, but these guys keep calling ecological economists Luddites because they want to stop growth. They want to stop the growth of consumption. And we need a democratic government. If we're going to do this, it has to be democratic. We have to get there democratically. Where do I want to go with this? I want to get to this to the conclusion, but the bottom line is, how much is a whale worth? And so economists will sit around the table. They decided that a whale is worth $2 million per large whale. This is because of their value to us. Okay, all I can say is, from the world's perspective, large whales are invaluable. They do ecosystem services. And they're invaluable to the biosphere and to the world that exists today. Economists have absolutely no value whatsoever. We can put them in Elon Musk's rocket ship sent on Mars. The world would be fine. Even to humanity, a group of experts who cannot foresee the greatest economic crisis of all time are functionally useless. Okay, this is why whales are valuable. There's a biological pump. That pump, remember I talked about the nutrients falling off the land. Well, there's biological pump that pumps those nutrients back up onto land so they get reused over and over and over again. This is called the phosphorus and nitrogen cycles. Okay, definition of capitalism is an economic system based on the private ownership of means of production and their operation for profit. And when, as has been the case for thousands of years, human labor was the means of production. Well, that's equivalent to slavery. Okay, let me just move right to the conclusions. Okay, so this is where we are. This is what we need to the energy we need to support 8 billion people with a decent life. This is what we're using, and 8 billion people don't have a decent life. Coal, to all my friends who think that we're growing solar and wind so fast, coal was the fastest, grew the most since 2000. The other thing of note is that we've never replaced one energy source with another. Okay. And I'm going to point out that that efficiency gains, these are efficiency gains. This is from the IEA, and you can see the more efficiency gain, the more we make the economy efficient, the more we use energy. And this is what was noted back in 1865 by the engineer William Stanley Jevon. Okay, nuclear power. One more thing to say about nuclear power. It grew exponentially here, 30% per year, enormous growth, and yet nuclear power is barely 2% of the total today. Look at coal. Okay, so just because wind and solar are growing so fast today, that means we had one solar panel last year, now we have two, so it grew 100%. That's irrelevant. Here's the price of lithium. Went up an order of magnitude in 2022. I think we have to do this. I'm not saying that we just should blow it off, but I'm saying it's challenging to think that we're going to be able to replace fossil fuels, okay, without just reducing the total amount of energy we have to replace. Wind and solar are the most expensive energy sources. We always hear how cheap they are, but when you add the fact that they have backup, they don't work all the time, they become the most expensive because you have to pay for the backup. And they're not doing it, they're not accounting for that. Um, uh, there's fusion and there's fission. This is a pretty cool cool. This is how the universe works. This is how our sun works. And of course we can do this easily because this happens naturally. U-235 and U-238 decay, but this doesn't, and it's hard to make happen. So fusion is going to be difficult to happen because we have positive deuterium and positive tritium, and you got to put them together. And it's like I said, putting two um, um, North Pole bar magnets together. It's hard to do. You got to overcome the Coulomb force. But radioactive decay of uranium happens spontaneously at all temperatures. So all we have to do is control it. It already happens. It's easy, and we have to speed it up enough that we can boil water, but we don't want to heat it up too much, so much that we blow ourselves up. And so it's a control theory problem. This is more difficult. This is a physics problem. This is just control theory. The other thing about fusion is that you always hear that oh, if the fuel is unlimited. Well, it isn't. The only thing we can actually do is deuterium tritium. Okay, we got plenty of deuterium. We know 2% of all hydrogen on the planet is deuterium, but there isn't any tritium. It doesn't occur naturally on Earth. And yet we have to do a deuterium tritium reaction. This is the reaction rate. Here's deuterium, and deuterium helium. They're way down here. So you can't not do this. And the total tritium reserves on Earth are 20 kilograms. The ITER experiment, we use 300 grams every day. So we've got 2 months worth. Where does our tritium come from? It comes from fission reactors. It's a byproduct of fission, an unwanted until now byproduct of fission reactors. It has a half-life of 12 years, so it doesn't even hang around very long. That's a problem. So we don't actually have a ready access to fuel. And I can go on, and this is more stuff we can talk about. But I want to get to the punchline because that's copper mine in Chile. This is a lithium mine. Everybody wants to be a Norwegian. Maybe this might be interesting to you because you hear this all the time. 80% of new cars are EVs. Oh, great. Of course, they have a government subsidy. What pays for that government subsidy? Oil and gas. 100% of their electricity is renewable anyway because Norway is blessed with hydroelectricity capability. Them and Costa Rica. And pretty much that's it in terms of countries that could rely almost exclusively on hydro. 72% of all primary energy in their point of view is renewable, and the world GDP, they're a wealthy country mainly because they export oil and gas to everybody else. Hydrogen economy is problematic. It's a small molecule, it leaks, and there's hydrogen embitterment. It creeps into tank walls and compromises the chemical structure, and it has a slow cold start problem. A lot of problems associated with hydrogen. Plus you need platinum, iridium, and these other rare and expensive elements to get it to work. So we're not going to do a hydrogen economy, and we're not going to do all these other things are problematic. To pull carbon out of the atmosphere, actually, to pull the carbon out of the atmosphere, one coal-fired power plant created, you need the energy from 6.5 coal-fired power plants. Think about that. Okay, so that's not going to happen, but that's the kind of thing we have to throw in to get to 1.5 degrees, all this fantasy and fairy tales. What do we do with the carbon dioxide once we pull it out? Well, in fact, we don't know. We don't have any good scale issues. Nuclear power is problematic, wind is problematic, solar photovoltaics, spark fusion reactors. Despite what they say, it does create waste that has to be stored. It's not the bad stuff like a fission reactors, but you need to keep it away for about 100 years, not trivial amounts. So this is the problems that we have. I asked one of my students, all my students, I had 400 students in the class, and I asked them all to write a comment or a question, whatever they liked. And I got a few, some of them predicted, gave multiple ones. I answered them all, every single one of them. I asked Ayush Mangolia. I liked her comment. I asked her to read it. Basically, she just reread everything I just said. In such a situation, what actions can we take? And I thought, oh my God, what did I teach these kids? And and but she hit the nail on the head. And then I says, oh, I got this other comment from Yash Gorkru. And I asked Yash to come up and read his comment to the class. So they're all in an auditorium. And he said, in the green and orange red graph on a safe operating space and boundary pie chart, why is stratospheric ozone depletion the least, even though the concern over ozone depletion has been prioritized a lot? Okay, I said, success. This is the solution. We did solve this problem. We have solved big problems. In the 1980, the ozone hole was in the red zone. This was met successfully by science-based government, international cooperation, standards, more regulation, and a moratorium. Okay, it was not met by capitalism or even, well, a little bit by technology, because we could get rid of CFCs because we had other chemicals. But here's stratospheric ozone depletion. It's now safely in the green zone. We can do this. It's just that we have all these things, and they're so far, it's going to be awfully difficult to do. And we have to do it quickly because we're running out of time. We're already in high risk. uh, so but we know the path forward. We know we need to listen to science. We need to get our engineers on it. And ultimately, we need to degrow the economy. We have to degrow the economy to get all these things back within the safe operating spaces. There's no technology that's going to be able to do this within the 30 or 50 years, the time limits that we have left. And then we have other regulatory successes. This is not the only one that regulate human misbehavior. Whales were saved by the IWC, by standards regulation, a moratorium finally in 1982. The African slave trade was abolished by an international moratorium imposed by Britain and France. So why did this happen? Well, the population, this guy Payne, I think his name was, he was a marine biologist, and he heard some quirky sounds in the ocean. Turned out to be whale songs. He recorded it and made a recording back in the late 70s, and it became a hit. It became a bestseller, and people all of a sudden were aware that whales actually existed. And actually, these are really cool, and they put pressure on their elected officials that, hey, we want to save the whales. And so the elected officials went to the IWC, who was reluctant. They wanted to, this is the whaling community, they wanted to just pump the oceans dry of these things. He said, no, look, we're not going to get reelected if you keep doing that. And bada boom, it was public pressure. And it was that guy, the Payne, and it was marine biologists and ecologists and environmentalists that forced saving of the whales, although they're not saved yet. Okay, but they're on, but at least we've made progress in that direction. African slave trade. In Britain, the people got fed up with slavery for whatever reason. They rose back in the early 1800s to a better level of morality, and they demanded that their government because they were buying all the cotton from the South, and they got upset that their cotton was tainted with slavery, and they put pressure on England. England then put pressure on France, and they abolished the African slave trade, which was quite lucrative to capitalism. So capitalism was just eating this stuff up, was making lots and lots of money on the African slave trade. And finally, of course, it took a civil war, the bloodiest civil war in our history. Waterfowl were saved by two acts of Congress, effectively ended commercial hunting and increased habitat protection. Polar bears were saved by the Marine Mammal Protection Act. Eagles saved by the EPA enforcement of the DDT ban. Elimination of acid rain, control of mercury emissions, and so forth. In other words, all these, And back then, back in the day, the United States had some juice in the world. You know, we were respected. Not maybe not so much anymore after Bush invaded Iraq for no reason whatsoever. But back then, our EPA enforced the banning of DDT, and it went global. And it wasn't just eagles, but it was all these large birds, um, polar bears. In fact, this is a U.S. led effort, and polar bears were not, but it's an international thing. It had to be international. Um, that's all these things. So we have successes. We know how to do this. We okay, we can do this. And that was my lesson to my students. Okay, then here's where we are now. I just downloaded this today. This is last year, and this is this year, and this is the global surface ocean temperature. This has climate scientists in an absolute panic. Okay, the chief scientist at NASA Goddard just wrote a paper, Gavin Schmid, in the journal Science, and he says we can't explain this. We don't know why this is happening. Okay, okay, it's worse. It's worse than everybody even ever possibly thinks. And here's last year's. This is surface temperature, and then here is this year. I'm missing a couple of days, I guess. Okay, not so bad, but it keeps going up. Plans, we got plans. Everybody tells me, oh, Paul Hawking a drawdown, but drawdown, he doesn't know anything about water. These are great. I mean, I really appreciate that. These are mostly all engineers who sat down and said, how can we get rid of fossil fuels with solar and wind, right? Basically. And they put together, okay, we got to get this much solar, this much wind, we can do this, we can do that, except that there's a lot of fantasy involved in these things. They're not looking at everything. And but they all come to exactly this conclusion. They don't use exactly these words, but they all have a statement like this. It is increasingly clear that averting ecological breakdown will require drastic changes to contemporary human society and the global economy embedded within it. Drastic changes to the global economy. We just can't keep doing this, what we're doing. We can't keep doing capitalism and assume that markets are going to get us out of the problems that they cause. And so at the end, these are not solutions. Before we see the solutions, BECS is ridiculous. Biofuels, well, it creates greenhouse gases, but requires land and water beyond belief in synthetic fertilizers. Geoengineering, forget about it. It reduces NPP if we start putting shades on the sun. DAX requires energy. I talked about that. It's insane the amount of energy this requires, and nobody talks about it. They always talk about how much it's going to cost. I don't care. We can print the money. it's the energy. Efficiency gains are not going to, we saw that. The more efficient we make the economy, the more energy it consumes. And that goes back to the maximum power principle. If you will, and if you read that paper, you understand why efficiency gains don't work. Carbon market offsets, that's like dieting, but by eating the cake and letting somebody else starve. A fusion, it has its problems. And agriculture, okay. Agriculture all by itself will blow past 2 degrees, even if we solved everything else. So we need to reduce agriculture emissions. Regenerative agriculture, all these things work. We know how to do this, but it's going to require government subsidy to help farmers transition off of all this chemical use onto this stuff. I recommend Gabe Brown. He's a farmer. He farms 5,000 acres in North Dakota. He's been doing it at it for 40 years. He almost lost this farm due to 2 years in a row hail 40 years ago. And he was forced to take some government subsidy that he found and to start doing regenerative organic agriculture just to survive and to keep the banks off his back. And he found out that he could become more productive. And so, but he's doing 5,000 acres. And so he's managing a farm as big as any farmer around, and he goes out and gives talks, and he's talked to Congress. He says, we can do this. I don't know how to do it, but and he wrote a book. A book is very interesting to read. Um, so we have to do that, and because agriculture right now sources about 25% of our greenhouse gases. Okay, we have to get rid of billionaires. We just can't afford them. They just use too much energy and they waste it. This is pure waste up here. You know, this is how much a person needs. This is how much they're using, right? And that's the average over the top. 10% billionaires are way above that. Okay, um, we can't afford them. And the problem is we're living in we're living in an oligarchy, because these guys meet every year in January in Switzerland and in Davos, and they tell the politicians what they want. What do they want? They want tax cuts for the billionaires, um, and they want the government to stay out of the private affairs, the businesses. So they know how to make an extra $1 billion. The historian of Harari points this out, but they don't know how to solve our problems. Okay. And then there's a system, government regulatory authority. Nixon's legacy is enormous. I know a lot of liberals don't like Nixon, but he was probably our best environmental president. And pre-Reagan examples I mentioned too. Reagan's and the conservative movement since Reagan has tried to kill Nixon's legacy, his good legacy, not the one that he was a crook. Reducing aviation emissions, we can do that. It's not easy. China has 45,000 kilometers of high-speed rail growing at 3,000 kilometers per year. We don't have any. This is China's high-speed rail network. China's, by the way, this is as big as the United States, including Alaska. It's a huge country. And they have 4 times as many people, but the area they cover and is just as big, and it makes sense. We can do it too, especially on the East Coast or West Coast. It makes a lot of sense. And I looked at the schedule. To go from Beijing to Hong Kong takes 8 hours. Okay, and then I looked at a plane schedule from Washington, D.C. to Dallas, but I couldn't get a direct flight, which was 2 hours and 45 minutes at the time that day, but there was a whole lot of one-stoppers, and they took 8 hours and 50 minutes. They took the same amount of time to fly, the same distance. So, you know, we can do this. And by the way, China, because they proactively did this, they have 85% of the IPR associated with high-speed rail. So we have to go to them if we want to build that high-speed rail. Okay, the solution is social democracy. Remember I said between capitalism and communism, the two extremes, there's an infinite number of possible economies that exist between them. It's not like we choose between these two. And this is what Bernie Sanders likes. You know, he calls it social democracy. This is a solution. Another name for it is moderation. You know, think of the Greek poet Hesiod. Observe, do measure. Moderation is best in all things. Globalization is not a bad thing. It makes us more resilient. I think it's a tool. It's like a hammer. You can bash your neighbor upside the head, or you can build a house, right? And in any way, it's inevitable. We've been globalizing ever since Homo erectus ventured out of Africa 1.8 billion years ago. So we are globalizing. We're a global species. But localizing too, enhance the local economy, personal freedom and responsibility. So these are characteristics, and that's just a bunch of words. What does it mean in reality? Well, okay, we need a wealth tax, a very large one. We need to break up large corporations. We need high-speed rail, regenerative agriculture. So we know all the stuff we have to do. Eliminate single-use plastic, not plastic altogether, but certainly single-use plastic. Redefine economics. Okay, we have economic models that work, so there's no reason to do neoclassical stuff. Eliminate defense spending. In order to do that, we're going to have to get along with each other. But you know, really, we have to try. We have to figure out how to do that. And we've made progress there too, because we started League of Nations after World War I. Well, that was kind of a flop. It was the first effort. After World War II, we come up with the UN. The UN has been fairly successful, not as successful as we would like, but it's a step forward. And so why not do the third next generation of a global kind of governance. And we're doing that. We have the International World Court. We have things. We have tools. And we need strong central democratic government. Remember Reagan said government is the problem. Well, no, government is not the problem. The government is us. We live in a democracy, although Reagan maybe wasn't aware of that. Government regulation of destructive business activities has to happen, and degrowth. We can only get rid of fossil fuels if we get rid of the waste that we're creating with our economy. What do they call it? Planned obsolescence, right? Everything in your house. I mean, I have a box of cable over the last 20 or 30 years. Where did all this cable come from? It's all this crap that I've been accumulating, and I don't know, it's frustrating. So what do we have to do to save ourselves? This is a bunch of stuff that will not work. I'm sorry. Technology is not going to help, general artificial intelligence, but this is what we have to do to save ourselves. We have to save ourselves. That's the only thing that's going to work. We have to all work together, and we do this cooperatively. Can we do that? Well, there's evidence that we have had success there. Maybe not much, but made some good progress. And then I tell my students what you could do if you want to be a really good engineer is always ask what could possibly go wrong. You always have to assume you could be wrong. Be curious, care, and then of course be kind, be kind, be kind. And critical thinking. Critical thinking is you're not to think critically is not you're not any smarter than an ideological thinking. You're just willing to be wrong. You try to talk to an ideologue and you're talking about a wall, you know. Anyway, I'm done. I got tons of backup, but we're not going to go there. And I really appreciate your time and in listening to me all this time. And I apologize for taking so much of your time. I hope you learn. I hope you helped or learned something. And I'll take comments or criticisms, anything you want.